All right, so we covered some series and parallel circuits. Let's do a little bit more about parallel circuits. Just to recap, resistance is it's added up with the inverse of the sum of the inverses formula. Voltage is common across each arm, and the current is additive. So I got a chart right here that I made. We have 12 volts of applied voltage. R1 is 1 kilo ohm, or 1000 ohms. R2 is 2.2 kilo ohm, or 2200 ohms, and R3 is 3.9 kilo ohms, or 3900 ohms. And we need to find all of these values. Right off the bat, we're going to fill in the givens. This is stuff that we're given by the exercise. So we know VT. VT is 12 volts. We know R1. R1 is 1 kilo ohm. R2 is 2.2 kilo ohm. And R3 is 3.9 kilo ohm. So now we need to find fill in all the blanks. Now we do know the voltage across each resistor. Okay. Now, even though I have it drawn out like this is still a parallel circuit. In the last exercise, it was drawn out a little different. It's not a big deal. This is still a parallel circuit. So we know that the voltage across R1 is the same as the voltage across R2 and R3, and that's the applied voltage, which is 12 volts, because voltage is common. So now, since we have the 1 k ohm and the 12 volts, and we have all that, we just need to find the current going through each resistor. And that's easy enough. We'll just use a calculator and my handy Ohm's Law card. So we want to find the current of going through R1. So we use our Ohm's Law card, we cover up the I, and that leaves us with voltage divided by resistance. So that's 12 volts divided by 1000 ohms. And that's 0.012. 0.012, and the unit of measure is amps, and that's equivalent to 12 milliamps. Let's do the same thing over here. 12 volts divided by 2.2 k ohms, so 12 divided by 2200, and that is 0.00545 amps. Now I like to use at least 3 significant digits when doing this kind of math. And so this would round to 5.45 milliamps. Okay, I hope that makes sense to everybody. So remember, 1 milliamp is equal to 0.001 amp. So you just move the dot 3 spaces, and there it is, 5.45. Okay. And then for R3, it's 12 divided by 3900, and that is 0.00308. So 3 significant digits. So that's 3.08 milliamps. So our IT current total current should equal the sum of these three. So approximately 12 plus 5.45 plus 3.08, approximately 20.53 milliamps. But there's an easy way to check that. So all we have to do to check it is find the equivalent resistance, or RT, of these three. Now remember, when we're doing that, we're pretending essentially that we're measuring with our meter right here. So what would my meter read if I put it across this resistive network, essentially? So let's get my scratch paper. And so R1 is 1000 ohms, R2 is 2200 ohms, R3 is 3900 ohms. And remember, the formula is going to be 1 over R1 plus 1 over R2 plus 1 over R3. So that's going to be 1 over 1000 ohms. Remember, always keep your units, always. And then 1 over 2200 ohms. And then 1 over 3900 ohms. And we could do that math pretty quickly and easily. 1 divided by 1000 is 0.001. And that's mhos. Okay? Remember, mhos is a unit of measure of conductivity. It's the inverse of resistance. Resistance is measured in ohms. Conductivity is measured in mhos. Or Siemens. Either one. But in this exercise, we're going to use mhos. And then 1 divided by 2200 is 0.000. Remember, I want to use 3 significant digits. Okay? It's important to have significant digits. That way you don't have a rounding error. And then 1 divided by 3900 is 0.00256 mhos. And we add all those up and divide it by 1. So 0.001 plus 0.000454 plus 0.000256. So 0.00171. So I want to do 1 divided by 0.00171. That gives me 584.8 ohms. So my equivalence will be 584.8. Alright, now remember, we conjectured that my total current would be around 20.5 milliamps. And now we can check it. So to do that, again, I'm going to use my Ohm's law card, cover up the current, so I have voltage divided by resistance. So that's 12 divided by 584.8, and I get 0.020519, or 20.52 milliamps. And that's pretty close to what we figured it would be just by adding the currents of these resistors. And I'm going to count off the 10 microamps between the two in rounding error, because we did only use 3 significant digits, and that's good enough. If you're in a class or you're working on a personal project, 3 significant digits should be enough. Now, if you are working on a precision project where you need to know exact resistance, you don't have a lot of tolerance, okay? Then I would use 6 significant digits. See here, the total current between these threes is 20.53, and we got 20.52. And if I did use 6 significant digits, it would be much, much closer. Let's do some analysis on the math. We'll get rid of that scratch paper. You see, the circuits that have the higher resistance have the lower current. This is something to consider. So 1K ohm had 12 milliamps, where the 2.2K ohms had 5.5 milliamps. So that's a almost double or more than double the resistance and less than half of the current. Okay, there is a relationship there. Same here, almost double the resistance and almost half of the current. Again, there is a relationship there. Okay, something to really think about, try to wrap your mind around. Remember, resistors, capacitors, transistors, diodes, all these devices and discrete components are only tools so that we can manipulate electrons. And electrons are physical objects. You can't see them, but they are there. And all we're trying to do is manipulate the way electrons move. Okay? So also remember, the total current going in should be the same going out. That's important. If the current across these three didn't add up to that, we did something wrong, and you should go back and check your work. Also remember that the applied voltage of the parallel resistive network is the same. It's common across each arm of the resistive network. So this is 12 volt, this is 12 volt, this is 12 volt. If you have any questions, leave them in the comments below, and have a great day.